All right, that works? Okay. Thank you everyone for coming. I think you'll notice that the talk's in English. I hope that's okay. I don't speak Bulgarian, and my Dutch will probably be incomprehensible as my German and French. So we'll stick to English. The talk will be quite technical. It's about a project I did at my university to get some grades instead of doing some optional courses. And this was a lot more fun. So it's called Tracy. Basically, it's a library to trace and inject system calls, which might sound very technical, but I'll start with some background and motivation for the project. Then I'll speak about some features that the library has and what you can do with it. I'll discuss some implementation details. This is quite technical, but all the other parts should be quite easy to follow, I hope. I'll discuss some future applications because it's a library and we want to do stuff with it. And finally, some future work for the project. Okay, so first of all, what we wanted to make is a library that you can use to trace system calls on most Linux architectures out there, and eventually also BSD. But it turns out to be quite hard because the main interface to debug processes is called DTrace. And it's not cross-platform and it's not cross-architecture. It's implemented in most of the platforms and architectures, but in a different way. And obviously, some different computers have different registers. Like your smartphone is a different CPU than your laptop, most probably. So that makes it quite hard to get all the values right. And on top of that, Linux and BSD also differ in the ptrace API. So it's not, you can't write a simple C program that will just use ptrace and then be able to debug all the processes. So a few possible use cases for the library to show you what you can do with it. And then I'll discuss how it works. So you can do jailing on a process-based level. So what you could do is you could look at what files the process opens, what kind of network connection it makes, and disallow them or rewrite them or change them so you can effectively make it open a different file or tell the process that the file isn't there even though the file is there and the process won't notice. You can do routing of I/O. You can send all the socket traffic over a proxy. You can do some nice debugging with it, visualization of system calls, replaying certain system calls that might be interesting for reverse engineering as well. You can do fault injection, which is simulate errors in your program. For example, simulate that the disk is full, and then see how your program reacts to the disk being full, because this is not something that happens very often, so your program might crash if you didn't write it properly. And you can do lots of logging as well. Okay, so very basic, a system call is it's the fundamental interface between an application and the kernel. So if you want to interact with hardware, then you need a system call. If you want to if you want to mount a hard disk, if you want to write to a hard disk, if you want to start a new process, if you want to open a file, if you want to chat with a process, you need a system call. And a system call is just a way to talk to the kernel, and you tell the kernel that you want it to do something by either executing a special instruction or equivalently an interrupt, depending on your platform. For example, there's the open system call, which you use to open a file. Then, with whatever open returns, you can write to a file. You can create a socket. You can fork, which is duplicate my process and then do something else with it. Or you can wait on specific signals of a process. And there's lots of other system calls, but these are basic common ones. So I mentioned ptrace already. It means process trace. It doesn't mean POSIX trace, which would imply that the API is sort of sane and shared, which it's not. So it doesn't mean POSIX. And as I said, it has no uniform API. And with ptrace, there's basically two ways to debug processes. You can either trap on every instruction, which is every assembly instruction executed, which is quite slow because every time you're debugging a process, the kernel has to stop the process. It will tell you, hey, it executed one instruction, and then you can do whatever you want with the instruction, with the process, and then you can let it continue to the next instruction. But this is very, very, very slow. So I think it will be at least 1,000 times slower, probably more, because the CPU has to do a lot of context switches and move your process onto the CPU and the other one out of the CPU. So that's not viable in this case, and we don't need it because ptrace also allows us to just trap on system calls and signals, which means that whenever the process you're debugging performs a system call, so performs the assembly instruction to says, hey, I want to do a system call, or receives a signal, which is, signals are just unique signals. And then the process is also stopped, and you can do whatever you want with it, and then have it resume or not, if you wish to. Okay. And Tracy uses ptrace on every platform that we support, because ptrace is the way to debug processes, and Tracy is not a ptrace replacement, but it uses ptrace to give you a nicer API to debug stuff. Okay, so like I said, it allows us to trap on system call instructions, and when the process is stopped that we're debugging, we can do anything with it. We can change the memory contents, we can look at the CPU registers that we're allowed to access, so does the process. We can change them, which means we can change a lot. We can change the arguments to a system call, we can change the system call number, which is a number in the register that defines which system call is to be executed. For example, read could be number 1, write could be number 2, and you can just change them and then the process will execute a different system call. We can also control the signals sent to the program. We can change signal numbers, which is funny, but I didn't find a good use for it yet. And obviously we can spawn new processes or already trace new processes created by the process we're debugging, because that's quite useful. If a program creates a new program, then you also want to debug that one, or not, but we can do that. Okay, so I'll just open all the features. Like I said, well, ptrace is event-based because you're waiting on a process to do something, for example, a system call, and then you can change the process. So Tracy is obviously also event-based. You can say, hey, I want to hook on a specific system call, in this case, a read. And then whenever the read system call is executed on a process, Tracy will invoke the function called readHook with the ID of the stop process and some other information. And you can just do whatever you want with the process. So a very nifty feature we build in, apart from just tracing system calls, is that you can inject system calls, which means that the process is stopped. And for example, it was trying to open a file, but meanwhile you wanted it to do something else, like create a network socket. Now when the process is stopped at a system call, you can just change the system call number. You can change the argument, say, hey, I want you to create a socket, and then you can have the program execute this system call without the process finding out that it has executed this system call. I mean, you can figure out if you try really hard, but the idea is that it's transparent. So what we'll do is we change some numbers, and we perform the system call, and then the program will resume with its open system call or whatever it was doing before. We also have an API to access memory in a fast way, because the Linux kernel, I think, now offers 3 ways to read the memory, and some of them are supported, some are not, and some are very slow, and some are fast but very recent. And we support the 2 Intel instruction sets and the ARM instruction set, which is what all your smartphones and embedded machines run. And there's some experimental bindings for Python, but I think they're broken right now because of some recent code rewrite. Okay, so just terminology. A Tracy is a program that is being traced, so a process that we are debugging. And a tracer is, for example, what Tracy is doing. It's tracing a process. So even though Tracy sounds the same as Tracy, it is in fact not the Tracy, it's a tracer. Okay, performs a system call. It will stop the program before it executes the system call, and after it has executed the system call, which means that you can, first of all, inspect. For example, if a process is performing the open system call, you can see what file it's opening and in what mode. And after it has opened the file, or not, you can read the return code, and you can see, okay, so this file descriptor was returned, or this was the error because the file was not found, or whatever. You don't have permissions. So what we do to inject system calls is we first of all look in which state we are. So if we're before the system call, we have to do something different than if we're after the system call, because we allowed you to inject. So But it's typically like this. So the programmer tries to perform a system call. It's a system call number. We can implement which is. And when this is the system, hey, this is our own system call, we're injecting it, go ahead, we stop getting our system call, and then we can restore the state. Injection, we differentiate between, you can do a synchronous injection and asynchronous injection. We'll inject the system call and wait until this might not be very nice if you're tracing and merge operation. Then you don't return immediately, and when the system call is actually finished, it will call your function, and then you can do whatever you. So this is the injection if execute a system call but hasn't yet registers before. Then we can change, and then we will restore whatever the result of our injected system call is. Then we will modify the instruction pointer or program counter, which is basically the number that will tell the CPU what instruction, because we've just executed the system, we'll have to jump back some bytes to execute the system call. And then the registers. Okay, so I briefly different way using ptrace, writing and reading a text map. ptrace is also a system call and virtual file system which basically contains process information and some other information, and each process identified by PID, which is a process ID and number of your program running, has a special mem file which is obviously not created by the program, but which you have if you're tracing a program. So this is also, you can write megabytes at once if you want. And enough. And there's some techniques to share some of your own memory. So memory that you can, some string tries to open, but if you wanted to open a different file in the Tracy, you change the system arguments, and yeah. The memory is read only for the Tracy and read write for us, because then we can change it. Another problem we run into when we were trying to add BSD support, we haven't finished this yet, but we're still working on it, is that if you create a new process, so if you're tracing a process, which is done very often, and it's in fact the only way to process, then you base that if you're trying to jail processes and make sure that the new process could remove some stuff, then you can't, like 6 years. It's originally written in Linux, but it should work. You just create a new program, and then the program is created, and at some point you will receive the ID of the newly created program, and then you can do whatever you want with it. The problem is that if you create a new program, it will already start running, and it's not guaranteed that you will get the number of the program before it's actually running. So it can do, like I said, lots of nasty stuff. So our idea was that we would create some controlled environment where the fork system call will be executed, and then both programs will do absolutely nothing. And we can then just wait until at some point we get the number of the new process, which is usually very fast, but and then we can take those two programs out of the controlled environment again and put them back where they were running originally. So basically we're creating some safe jump where the programs will run indefinitely and do absolutely nothing, and then we place them back at the original point, and then we're already tracing both the programs. So it's encoded, looks very simple. So the idea is that the fork system call is executed. So then we go from one process to two processes, and they're running at the same time. Then the number will be sent by the parent at some point when it's resumed. So we get the PID number. The child will not do this, so it will just end up going in a loop, performing the scheduled system call, which means do nothing, let other processes do stuff. So what will happen, say the parent creates a process, the child is already running, it's faster, the scheduler said, hey, the child is nicer, go and do something. The child will just keep running in the scheduled loop, and it can't do anything, and the original program isn't even being resumed, it's just staying there. And the parent will end up there as well, but it will then send us the number of the child, so then we can attach to the child and safely put it back at the original place. Okay, so there was another big problem that we ran into, and we originally didn't solve it, but I recently coded quite some stuff in to be able to cope with it. And the problem is that Linux supports multiple ABIs, and an ABI is an application binary interface, which basically defines how you pass your system call numbers, what the system call numbers mean, and how you execute them. So the instruction determines the ABI, which kind of makes sense. For example, the new Intel processors running AMD 64 They support the old 32-bit processes as well, so all the old instructions are also supported. And if a program runs in a 64-bit mode, it can still execute a 32-bit instructions. So if you execute a 32-bit instruction as a 64-bit program, then the system call numbers have a different meaning, which means that so the system call numbers are different for 64 and 32-bit. And it's very hard to determine if the process is in 64 or 32-bit mode doing a system call. So there's another register that also has an effect, the code segment register, but I'll not go into that. And like I said, processors can mix the ABIs at runtime, which is really, really bad. And it's really hard to debug this. And astrays does it wrong. Oh, something I didn't mention before, but it might be interesting. For the whole safe fork problem, if you read the astrays manual page, astrays is a program that will allow you to trace system calls. Astrays just literally puts in the manual page, so we don't know when the child attached to the child, but it can do lots of stuff. Some calls are executed. This is very, very useful, and it's a very nice program. I'm happy that it exists, but the code is absolutely terrible. It's quite large, 25,000 lines of code, and all the C files are just large files for all the architectures mashed together, so there's no file for Intel instruction sets. Okay, so this is an example program which is compiled as a 64-bit program, and what it does, it will simply call a system call, in this case using the Intel instruction for a 32-bit process, which means the system call numbers will be different, and it will just execute a system call, which is one of the most simple system calls, give me my process number. And astrays will see something completely different. And this is the output of astrays, which is basically a wrong system call number, and you can see it gets lots of errors because it tries to read addresses that don't exist, and yeah, it goes pretty bad. Tracy does it properly, so it does detect that. In fact, we are seeing a get_pit function. So this is something I should probably file a bug with them, and I know how to fix it, so I might just file a patch. So the clue here is that the system call number 20 is get_pit on 32-bit systems, but on 64-bit systems is the write key system call. And astrays didn't detect that it's in a different mode, so it just thought, hey, it's write key. A problem here is that right now, change the system call instruction we're trying to read. So in this case, it can change it from a 64 to 30-bit instruction, then we have a problem. This is something I haven't solved yet. So if there's a malicious program out there, it can still fool Tracy. But you won't find that quite often, I think. So an idea here would be to make the memory either readable and executable or writable, which means that you can't execute and write to the memory at the same time. Then a thread is unable to change the memory when you're, in fact, when another thread is executing it. But this is very hard and will take a lot of code, and I tried to keep Tracy relatively simple, so we didn't implement this yet. Okay, so an application for Tracy is something we call SOXY. It's a transparent proxifier using SOX5, and SOX5 is as you might have guessed, a protocol to proxy stuff. And it's like TSOX or TORSOX. So the idea is that you open a connection to a proxy server, you send some magic bytes saying, hey, this is me and this is my authentication, and I want to send lots of data to the socket. And then once that's done, you can just send socket data like it's normal socket. So then the connection, it isn't clear that you're talking to a proxy because the only difference is in the initial state, and then you can just send all your data. So this is very nice if, for example, with TSOX or TORSOX, you want to reroute sockets and internet traffic. So there's this thing called LD preloads. I'll get back to SOXY in a second. And what it basically does is, this is what TSOX and TORSOX use. The idea is that to hook into a program, you have to insert some library, so you can override their read, write, and socket system calls, so you can catch whatever they're trying to do with the network and put it through a proxy first. So to do this, tsocks and torsocks use LD preload, and what it basically does, it loads their own library on top of libc, and it overrides whatever you want to override, and then afterwards you can call the libc function. So you can, again, change, for example, open arguments or socket arguments or any arguments to a call in the library. The problem is that if a program directly executes system call instructions, so it doesn't go through a standard C library, then this doesn't work. It doesn't catch anything, it doesn't see anything, so it doesn't work. For normal programs, this works, but if you want to jail stuff or whatever, this is not the solution. So we tried to do the same that torsocks does with LD preload with Tracy, and Soxy does exactly this. So Soxy is a bit buggy right now because I implemented all the ABI stuff, but it is usable. So the idea is that a program will create a socket, and it has some destination address like, hey, I want to connect to this. And please create the socket structure for me so I can start sending stuff. So what Soxy will do is it will then suspend the program. It will change the socket argument and connect to a proxy server. It will it will inject several system calls. For example, we'll write several bytes to say, hey, this is us, we're speaking SOX5, and we'd really like to transfer some data on the socket. And once the initial handshake is complete, then it will return to the original program and return a socket structure that does the proper thing. And then the program can just do all its read and writes on the socket, and it would have never noticed that it's in fact talking through a proxy. And this does not rely on any LD preload hacks, and it should be perfectly safe. So you can't break out of it. Okay, I discussed this. So during my bachelor thesis, which had some overlap with this project, I wrote a kernel patch that would really speed things up, because Tracy is definitely slower than LD preload and those kind of hacks, because every time a system call is executed, the process needs to be suspended, and you can do some stuff with it, and then you need to start it again. And there's a huge overhead in doing so, because for every system call, the process will be suspended twice, and you have to tell it to continue twice, which means that there will be at least 4 context switches, which means that the process running on CPU, it will be taken out of CPU. Your process will be in CPU. You can say, hey, continue, and then you're again taking out of CPU, the debugging process is in there, and then you do the same thing because you have a pre and post system call. This is really, really, really slow. So if you're doing a lot of read system calls, which is common, you'll just read like 1,000 bytes. This becomes very slow. So what I did is I wrote a kernel patch for the Linux kernel, which would allow you to use the ptrace API, which I extended with a few arguments. And you will be able to say, okay, so for these system calls, I don't want you to send me a notification, or I do want you to send me a notification of this system call. So in this example, it would say, okay, so there's 2 system calls, read and write, and I don't want you to send any information about these system calls, which means that in fact the system calls that are executed very often, you'll get no notification of them at all. So if you do this in astrays, you'll just simply not see any read or write system calls. And this is a lot faster. Okay, so some future applications. One of them is buggy. And this would basically change the results of your system calls and perform fault injection. So again, like I said, you can fake that the disk is full, or that you could fake that you're out of memory, which is something that does happen more often. Yeah, you can fake broken pipes and lots of stuff that can go wrong, and lots of stuff does go wrong, but very often programs are simply not suited, or they haven't seen all the problems. Another one is jelly. This would be a secure jail. So what you could then do is you start a program linked with Tracy, and it would start some program that you want to jail, and then all the system calls are intercepted and changed. For example, you can disallow network completely, or you can allow network only to a specific host. You can say, okay, so you can read these files, but you can't read the others, and you can't write to them. So in fact, you're making a very small virtual machine without the overhead of loading an entire new kernel, requiring hardware virtualization, stuff like that. That's pretty common. And the nice thing is that you don't need to be an administrator or root on the system, because you can do this as a user. So this is very nice if you have some program that you don't trust but you still want to run it. You can use Jelly. It doesn't exist yet, but when I find some time, I'll work on it. Another one is Fuzzy. This is actually the program that inspired creating Tracy. I wanted to write this program, but then I found that ptrace really sucked for different platforms. And the idea behind Fuzzy is that we want to emulate Fuse in user space. So I'll briefly explain what Fuse is. Fuse is an API on Linux, or it's a special file that you can use to create file systems as a user, so not as an administrator. And this is very nice. There's lots of different nice applications for this. For example, there's a file system using SSH, so you can just mount it somewhere, and then you have access to a remote server where you have SSH access to. And this is done through the dev Fuse file. But I've encountered quite some machines, especially on my university, which don't support this, which is really a shame because you're a user, but you can't use it because they didn't enable it in the kernel. So what we wanted to do is we want to track all the system calls of a process or multiple processes, and if they try to open dev Fuse, we'll just fake we'll fake all the interaction with the dev Fuse file. So then the program thinks that Fuse exists, but it actually doesn't exist, but we're implementing all the stuff required in our program, which means that outside of whatever we're jailing, you can't even see that it's mounted because it's effectively not mounted. But if you do it properly, then all the processes that you are tracing will see the dev Fuse file and wherever you mounted something. And then, in fact, you have, Fuse as a user without the dev Fuse file. It's quite complicated, but it's just funny. Right, and at some point we might write astrace, which is just a proper astrace. Some future work, I mentioned some of these things briefly. One of them is thread-safe ABI detection. Like I said, ABIs are very complicated on Linux. I don't even want to talk about BSD because it has some Linux compatibility layer, and I didn't read into that because I think it will also support all the different architectures that Linux does, or like 64 and 32-bit. But it needs to be thread safe, so it should be in a sense. So it should be like there's an instruction, and we want to read it, and it shouldn't be changed by any other thread that we're also tracing. So then we know for sure that this is this ABI that is actually being run. Okay, so there's also some research that I want to do, and that is how cross-platform and cross-architecture actually can become, because at some point it does get quite complicated, and I really hope that we could make a completely cross-platform and cross-architecture library, but it's really hard. For example, I mentioned that Soxy was a bit buggy with the new ABI support. One of the problems that you run into is if you're running a 64-bit Soxy and you're tracing some program that will do both 64 and 32-bit system calls, it will try to, for example, allocate a socket, but the socket will return a pointer, and the pointer differs per 64 and 32-bit in size. And also, lots of structures differ in size. For example, an integer is 8 bytes on 64-bit, or a long is 8 bytes 64-bit, and on 32-bit, that's only 4 bytes. So you'd have to do a lot of hackery to actually return the proper structures in the proper size, which is exactly what we didn't want, because we wanted something that was cross-platform. And you didn't need a lot of quirks to work around different architectures. I think there's something in the kernel, in Linux kernel source code, that does something like this to support 32-bit and 64-bit, but I haven't been able to find out what they're doing exactly. Again, time constraints. Okay, so I already mentioned safely tracing children on BSD. We call this safe fork or Champy. As soon as I get a working BSD system again, I'll try to implement this support. The kernel patch is there for speed, but I don't think it will be accepted in the main line because there have been some patches like this, and they don't really see the use for this kind of APIs, which is a shame. And there's now something different called secure computing, but it's annoying because you can only say, hey, I want to not get a notification for the read system call, but you can't change it at a later time, so it's really sticky, so you can't change it. That's really annoying if you're debugging you only don't want to get read system calls at some point. And finally, I want to see, which is again similar to research, if I can make some kind of system call intermediate representation, which would be some representation of a system call that you can translate to any kind of architecture that is Unix, like BSD or Linux or Solaris. So that means that you won't have several open system calls or whatever. It's kind of messy. Okay, so I think I'm actually finishing early, so that's very good news. I hope you will be able to you were able to follow this. So I wrote this with 2 friends at the university. The idea was by someone else. The code is freely online. It's GPL licensed. You can find it on GitHub. We have an IRC channel, a homepage in the form of a wiki, and the mailing list that is not being used very often. Okay, thank you very much. I hope it was a bit clear. And questions?
Any questions?
You didn't mention DTrace for BSD and Solaris.
So as far as I know, DTrace doesn't allow you to inject any system calls. So you can't change stuff and inject code. But it's nice for logging stuff, I agree. But this is a different use case.
Real question.
Hi, this is really amazing what you have done. And I have just one question. It is, okay, it's very funny that you should mention a SOX 5 application because I am right now actually working on an update to the Debian package of Dante, the SOX server client and so on. And I'm just wondering, have you looked at possibilities of using Tracy as an LD preloaded library to trace the same process? I mean, from a very quick search that I did just now, it seems that it is kind of funny to get Linux to use ptrace on a different thread in the same process. Have you examined that? Is there have you come across a valid use case for that, obviously?
I'm not sure if I completely got your question.
The question was...
So, about LD preload, but that's not completely clear.
Okay, well, from what I understand so far, you are using Tracy on a new process, on a different process. Have you looked into using it on a different thread in the same process?
Okay, I understand it. No, I haven't, but it's a really good idea, actually. I like it. So what you want to do is you want to take a Tracy application or library and inject it, and then run that code, and then infect the process from within. The problem is that you definitely need to create a new process, because if you want to trace your own process, then you're effectively tracing yourself, which means that we'll also be blocking on our own system calls, and if we're blocking on our own system calls, we can't tell ourselves to continue. So then we'll have to wait indefinitely, and that doesn't work. So you can't actually trace yourself as a process. But if you spawn a new thread, then you can say, okay, I want to trace you. I want to trace my parent, and that works.
My question is kind of similar. If you want to hook system calls as with fuzzy and modified their behavior, how does Tracy compare to LD preload?
Okay, so what you can do with LD preload is you can take any kind of library function that exists. For example, in libc, there's lots of ones that are named like system calls. For example, open, read, write, and stuff. They have some different parameters, but the end result is the same, which is that some system call is executed. But you can also use LD preload for libraries that are not default or that are not even using system calls. And Tracy is just working on a system call level, so it's a very low level. And the main reason to use Tracy over LD preload in this case is if you want to be absolutely sure that every system call that is executed is actually, that you control everything that is being executed. So the advantages are...
What are the advantages?
So the advantages are that LD preload is not safe. So if you want to write a jail, or you want to proxify everything, then LD preload simply doesn't cut it. So if you have this program and you want to run everything over Tor, Tor is an anonymizing network and you can use it via SOX 5 proxy, then you can't be sure if you're using LD preload that everything is going over Tor. And if you want to anonymize a program entirely, then you have to do it on system call level, because if a program executes some code, so if a program executes some code.
Sorry, I got it. I understand.
Okay, so very basically, if you want to perform a system call, you usually use glibc, which is the C library to interact with the kernel and do other stuff. That will call some assembly code that will perform a system call instruction. The code that will jump to the system call instruction is libc code, and LD preload will override that part. What you will do with Tracy is you will look at the next part. And you can avoid LD preload by writing your own inline assembly, which will just do a system call, which means that the jump to a libc function is never executed. So then you can't hook that part. And Tracy allows you to do it on a lower level.
Другие вопросы?
So you mentioned some of the problems with tracing the children's clone by the fork system call. What about the clone system call?
All right, so the clone system call is a bit harder, because with the clone, our fork is simple. You give it no arguments and it creates a new process. If you use clone, then you can give lots of different options, like, okay, so I don't want to share memory, I don't want to share my like my file descriptor table and other stuff. And you can also give clone an instruction to jump to, but that's actually only in libc. So the case is actually very similar. So what we done with safe fork is actually the same for clone. So clone can create processes in a different way, but it will still start executing at the same instruction, which is the instruction after the clone system call, and then we can still capture it. And then whatever happens afterwards is not a problem. For example, glibc will allow the clone system call to jump to another instruction or to some point in your program, but actually the Linux system call doesn't do it. So it's something libc hacks around it. So it's not a problem for us.
One more question. First come, first serve.
I was thinking about when you catch a syscall, to kind of send it over the network to something like a GDB server when you debug remotely. Did you think about this?
Are you asking if it's similar or?
No, have you thought about making a plugin system for this so you can actually...
Ah, right. No, I haven't. But it's another very nice idea. Thank you.
Okay, let's thank Merlijn.